the email arrives on a quiet afternoon and it is not from anyone you know. A site you signed up for 6 years ago and forgot about has lost its user table, and your address sits in the file that is being traded around today. You already know what you did with that password. You reused it everywhere. So how much you lose this week depends entirely on a decision you never got to make, what that site kept in its database on the day you typed those characters in. Not your name, and not your face. One field, one column, one string. What does a login actually need to know about you? Hold that question, because everything that follows turns on it, and we will come back to it at the very end. Say you are the one building the site this time. It is called Copperpost, a forum for people who restore old radios, and it has gone from 40 members to 200,000 rows in your user table in a year and a half. You have a sign-up form. You have a login form. You have one email column. Now you need a second column, and what you put in it is the whole of this episode. Before you choose, ask what you are actually afraid of losing. Is it that somebody watches a login request on the wire? Is it that one of your own 3 colleagues goes looking through the table late at night? Or is it the thing that has happened to almost every company you have ever given a password to, where the whole table walks out of the company at once and you find out from somebody else? That last one names the threat this column exists to survive. Every choice below gets judged against a single scenario. Your user table is now a file on a stranger's laptop, and you will never get it back. Here is the sentence you have probably written, or nodded along to in a review without turning it over. We will encrypt the passwords in the database. Simple. But that is not a mechanism, it is a reflex. Encryption is a two-way door, and it is built that way deliberately. You encrypt something because you intend to read it back later, which means a key exists, and whoever holds that key holds every password on your forum. So where does Copperpost keep that key? Be honest about the answer, because it is always the same answer. The key sits in the environment variables on the same machine, or in a config file the application reads at boot, or in a secret store that the application is authorized to open at will. If intruders can read your user table, they got there through the application or through the host. The key was standing right next to the data the whole time. Analogy: encryption is a safe, and a safe is a wonderful thing, but you have just bolted the key to the front of the door, because your own staff need to open it 400 times a second. Do you actually need to read those passwords back? Sit with that. When a member of Copperpost logs in, what does your code have to accomplish? It has to answer one yes or no question: is the string this person just typed the same string they chose when they registered? That is a comparison. It is not a retrieval. That single observation is the origin of the whole field. Once you notice that you never need the password back, you are free to store something that is not the password at all, and that is a strictly stronger position than any key management scheme you could build. So try again. Take 2. You will hash it. A hash function eats any input and returns a fixed-length fingerprint, and the useful property is that it only runs forwards. Given the string, you get the fingerprint in microseconds. Given the fingerprint, there is no arithmetic that walks backwards to the string. You store the fingerprint, you throw the password away, and at login you fingerprint what was typed and compare. Simple. But that is not enough either, and the reason is the most important idea in this episode. A hash has no way to be reversed, so nobody reverses it. They guess instead. Your attacker takes a word list, hashes every entry, and looks for matches in the file they stole from you. The question that decides whether they win is not whether your function is one way. It is how many guesses per second your choice of function allows them. Ask that about the family of hashes you already know. Those functions were designed to be fast, because their real jobs are checksums and signatures and content addressing, where speed is the entire point. On a single modern graphics card, one attacker runs billions of guesses per second against them. Against a fingerprint of your user's passwords, that speed is working for the attacker and against you. Case in point, LinkedIn in 2012 leaked around 6.5 million password fingerprints, made with SHA-1 and no extra ingredient, and a hobbyist community had cracked the large majority of them within days. Adobe the following year was worse in a different way, because Adobe had genuinely encrypted its passwords, in a block cipher mode that leaked which users shared a password, with a key the company kept somewhere in its own estate. So one of them was too fast and the other was reversible, and both failed in public, at the scale of tens of millions of people. There is a second thing wrong with a bare fingerprint, and it is subtler. If 2 members of Copperpost pick the same password, their stored strings are identical. So what does the shape of your table leak before anybody has cracked anything? It leaks which accounts share a password, which tells your attacker exactly where to start, and it lets them guess once and win many times. Somebody who has already run the RockU word list through MD5 and SHA1 does not even have to execute your function. They just index into a table they built years ago. Take 3. You add salt. For every member, you generate a random value, 16 bytes of real randomness, and you store it in the clear next to the fingerprint. When you fingerprint the password, you fingerprint the salt and the password together. Two members with the same password now get two completely different stored strings. Note, the salt is not a secret and it is not trying to be. Its only job is to make every account a separate problem. A pre-computed table built for the world at large is worthless against your table, because your table has 200,000 different problems in it rather than one. But look closely at what salt actually bought you, because this is where a lot of engineers stop and they stop one step early. Salt destroyed pre-computation and it destroyed sharing of effort between accounts. It did nothing whatsoever about speed. Your attacker who wants one specific account, say the administrator of Copperpost, still gets billions of guesses per second against that one salted fingerprint. So what is left to change? You have made the function one way. You have made every account its own problem. The only variable still on the table is time. Here is the move that earns this whole subject its own name, and it feels wrong the first time you hear it. You choose a function that is deliberately, tunably slow. Not slow by accident. Slow by parameter, with a number you set, and can raise later. Think about why that is safe rather than reckless, because the mechanism is arithmetic and not faith. Your server checks one password per login attempt, for one human being who is willing to wait a quarter of a second. Your attacker checks 100 million candidates against a single stolen fingerprint. So a delay of 250 milliseconds is invisible to your member, and it multiplies the attacker's bill by a factor that scales with every guess they have to make. That asymmetry is the entire product. You are not making the secret stronger. You are making guessing expensive. The functions that do this each expose the dial differently, and it is worth knowing which dial you are turning. Bcrypt, derived from the Blowfish cipher and in service for over 2 decades, exposes a cost factor, where raising the number by 1 doubles the work. PBKDF2 works by simply repeating the ordinary kind of hash, so it exposes a plain iteration count, and current OWASP guidance for it runs into the hundreds of thousands. Scrypt and Argon 2 expose something better than time, which is memory. Why should memory matter more than time? Because of what your attacker is buying. A GPU wins at password guessing by running thousands of tiny arithmetic units in parallel, and those units are starved for fast local memory. A function that insists on filling 64 megabytes for every single guess hands each of those parallel units a problem it has no room to hold. You have moved the contest off the field where specialized hardware wins by a factor of thousands and onto one where it barely wins at all. That is what memory hard means, and it is why Argon 2 won the password hashing competition in 2015, why the memory hard variants are what NIST and OWASP now point at first, and why the recommended settings are quoted as a memory figure rather than a time. Now let us walk the actual code path in Copperpost, because the mechanism is short and the details are where people get hurt. A member registers. You generate a fresh random salt. You call your chosen function with the password, the salt, a memory cost, a time cost, and a parallelism setting matched to your 4 cores. You get back a single string, and here is the part worth admiring, that string carries its own parameters inside it. The algorithm name, the version, the memory and time costs, the salt, and the digest, all in one field. You write that one string into your second column. You never write the password anywhere else, not into a log, not into the error message, not into the analytics event, and this is the boring failure that actually catches teams, because a password that reaches your logging pipeline has just been copied to every place your logs go. A member logs in. You read their stored string, you read the parameters back out of it, you run the same function over what they just typed, and then you compare in constant time, so the comparison itself tells nobody how close they got. Now notice what you did not need. Did you need a key anywhere in that path? You needed no key, no secrets manager, no rotation policy, and no plan for the day somebody reads your configuration file. That self-describing string is also your upgrade path, and this is the trick that keeps a system alive for a decade. When you decide the cost should be higher next year, you raise it for new registrations, and on every successful login you check whether the stored parameters are older than your current policy. If they are, you already have the plain text in memory, right there, for one instant, legitimately. So you rehash it at the new cost and write the new string. Your table upgrades itself as your members visit, and nobody is emailed and nobody is locked out. There is one more ingredient you may want, and it is worth naming precisely because it is often described badly. A pepper is a single site-wide secret value mixed in alongside the salt, and it lives somewhere the database does not, in the application configuration, or in a hardware module. It buys you exactly one thing. If somebody steals only your database, and not your application host, then even correctly guessed passwords fail to verify. Notice how narrow that is, and notice that it is real. 2 of the last decade's large leaks were database only. In practice, the pitfalls that bite real teams are almost never the choice of algorithm. Bcrypt silently truncates its input past 72 bytes, so a beautifully long passphrase gets quietly cut, and the documented fix is a pre-hashing step rather than a clever one you invent yourself. Some teams hash on the client to be helpful, which merely renames the secret, because whatever the server accepts verbatim is the password now. And a surprising number of outages come from a memory cost that was tuned on a laptop and then deployed into a container with a hard memory ceiling, so your login path may still fall over under load even though every parameter looked responsible in a spreadsheet. Caveat: a slow hash is a cost you pay too, and the attacker who cannot read your database can still point a flood of login attempts at you and watch your own work factor exhaust your cores. Is that a reason to lower the cost? No, but it depends on what sits in front of the endpoint. This control does not stand alone, so put ordinary rate limiting and lockout ahead of the login path before you tune anything behind it. Which brings us to the honest limit of everything above, and you should hear it plainly. Password hashing protects your users after your database has already left the building, and its value depends on that being the attack you got. It does nothing at all about the far more common one, which is credential stuffing. Somebody takes a password leaked from some other site and simply tries it on yours. How would your best chosen parameters help there? They would not, because the attacker is guessing correctly on the first attempt. What helps is checking new passwords against a breach corpus such as the Have I Been Pawned range API, watching for distributed login attempts across many accounts, and offering a second factor. And there is a direction beyond all of it that is worth watching, because it follows the same insight we started with. If storing something better than the password is good, is storing nothing at all better still? That is the bet WebAuthn and passkeys make. The member's device keeps a private key, your server keeps only the matching public one, and a stolen server database now gives the attacker material that can verify a signature and forge none. The lineage is unbroken. Every step in this story has been a step away from holding the secret at all. So which brings us back to the question from the top. What should that forgotten site have kept in its database on the day you registered? The answer is a single self-describing string that was expensive to produce, useless to reverse, unique to you even if your password was the most common one in the world, and worth nothing to whoever is trading that file today. If it had stored that, your reused password would still be your problem, but it would not be their gift. 2 things are worth asking yourself before you close this. First, if your production database were copied tonight, how long would one of your members' passwords survive, and can you name the parameter that decides it? Second, when was that parameter last raised, and does your login path have the 3 lines that would raise it automatically? If you find that you have a fast fingerprint with no salt, or a reversible field with a key sitting next to it, you now know what to do and roughly what it costs. The question is whether you would rather find that out from your own reading, this afternoon, or from one more email that lands on a quiet afternoon and is not from anyone you know.